In this video, we are going to take a look at a problem that involves the for all operator. So the question that we're given is, given an integer array f0 to n of Boolean, where n is greater than or equal to 0, write a specification and hence derive a solution that will determine if the array contains all true values. So let's look at the question first and see what information we can get from it. Okay, we know we're dealing with an array. Name of the array is f, the dimension is f0 to n. It's a Boolean array, and we're told that n, that defines the upper bound of the array, is greater than or equal to 0. So the array could be empty, or it could be a value of 1 or a dimension of 1 or greater. So we do have a situation where we could have an empty array by the fact that n is greater than or equal to 0. And we have to write a specification and hence derive a solution that will determine if the array contains all true values. So we're looking to check to see if the array contains all true values. So let's have a go at writing the specification for this. Specification will start off by defining our constants. So we'll have con n of type int. And when we have a look at what we were told about n in the question, we were told that n is greater than or equal to 0. So we write that in as an assertion about n. We're also told that we need an array. Now, the array in this question is not going to change. We don't need to modify any of the values in the array. So it can also be a constant. So we'll say f is of type array, zero to n of, and the type of the array that we're dealing with, as we were told in the question, is Boolean. Okay, so f is an array from 0 to n, where n is defined as being greater than or equal to 0, and the type of the array is Boolean. Okay, the next part is we're asked to write the specification. We're doing that now, but the thing that we're asked to do is check to see or determine if the array contains all true values. So at the end of this program, we're going to have an answer. So we need to have a variable to store the outcome of this program. So we're going to need to define a variable. So I'm going to have a section here called var, and then in here I'm going to define a variable called all true, and that's going to be of type Boolean. And then we can, for the moment, use a label. Let's just call it S. It's just a little placeholder for the program itself. And finally, what we need to do, of course, is write a post condition. So our post condition is going to be all true is equivalent to for all I, where I is greater than or equal to 0, less than n, f dot I is equal to true. And that is our specification. Now, we don't have to say f dot I equal to true. We could just simply leave it as f dot I. F dot I just on its own would we're assuming that f.I is true. If we wanted false, we'd have to say not f.I. F.I here on its own, because it's a Boolean, will be true if it is true. So we don't actually need the f.I equal to true here. We could just leave it as f.I on its own, but I'm going to leave the true equal to true in here just so there's absolutely no ambiguity about what we mean. We are looking to test to see if all of the values in the array are equal to true. So the f.I equal to true here makes that plainly clear. So the next thing we will need to do is we'll need to write down an invariant. So in order to write down an invariant, what we're going to do is we're going to look at the post condition, and we're going to check to see, is there a variable in here, or sorry, is there a constant in here that we can replace with a variable? So we have two choices really. The constants that we have are 0, we could replace that with a variable, or n, we could replace that with a variable. So if we replace 0 with a variable, we'll end up with a loop that loops from tail to head. In other words, we'll start at the end of the array and process towards the beginning of the array. If we replace n, we'll end up with a loop that starts at the beginning of the array and processes towards the end of the array. So we would normally process from the beginning of the array to the end of the array anyway, so let's look at replacing n with a variable in order to create our invariant. So our post condition is all true is equivalent to, for all I greater than or equal to 0 less than capital N, which is the n that defines the upper bound of our array, f.I equal to true. And we're going to create an invariant by replacing capital N with small n. We usually use small n as a convention here. We get rid of the capital N and replace it with a smaller n, and the small n signifies that it's a variable. So this is quite easy really. All we're going to do is rewrite out our post condition, and wherever there's a capital N, just replace it with small n. Now this will give us in fact two parts, which we'll have a look at in a second. I'll write it all out first and then explain what's going on. So our invariant then becomes all true is equivalent to, for all I greater than or equal to 0, less than, and we get rid of the capital N and we put in a small n, and we have f.I equal to true, and small n is greater than or equal to 0 and less than or equal to n. Okay, so once we replace the constant n with a variable small n, so the replacement has taken place here, so there's large N, there's small n. Once we do that, we're introducing a new variable, and this new variable is going to basically allow us to have an invariant. This is kind of controlling our invariant, because it's going to have a range, and the range that this small n is going to have, it's going to be allowed to be greater than or equal to 0, so it's going to start at 0, and then it's going to work its way up towards large N until it is actually equal to large N. Now it's very important to remember that this small n is going to allow us to control the loop, and we are going to use it in order to access elements in the array, but the loop will stop us from going out of bounds. So when we deal with this small n over here in this part of our invariant, we see that n is greater than or equal to 0, that's not a problem because our array starts at 0, but it's less than or equal to large N, which at first might seem a bit strange because we might think that we go out of bounds, but the loop will actually control this. The loop will stop us from accessing any elements that are past the end of the array. So this isn't a problem. In fact, it's necessary because after the loop finishes, we want small n to be equal to large N. So this is critical over here, that we allow small n to be less than or equal to large N. You'll notice in this part that it's I greater than or equal to 0 less than n. So as n increases, this part or this segment here will grow. So we end up with two parts really to our invariant. And usually we call these two parts P0 and P1. And it's with this invariant now that we can go and derive a solution to our problem. So one of the first things that we need to do is write out a little outline solution, which can be very helpful. So one of the first things we do with the outline solution is we say, okay, we have to figure out a way to initialize our variables, and we'll signify that as S0. It's part of our program. It's the first little bit of program code that we write, initialize our variables. Once we do that, that will establish our invariant P. And of course, when we look at our invariant, we'll have a bound function in order to make sure that our program actually terminates. So the bound function here will be large N minus small n. So the invariant P is really both of these parts together. So we can say P is the whole lot. P is the whole part P0 and P1 together, just to cut down on what we have to write. So we have P here and we have a bound function. So our bound function shows that we have a decreasing space to process every time around the loop, and n, capital N minus n, will give us a decreasing function, and we'll see that when we get on to proving our termination. So once we've established our invariant, then we can write our loop, and our loop is going to be do small n not equal to large N. Why is that? Well, we know that this has to be the case for our loop because we have replaced large N with small n, which means we're processing from the beginning of the array to the end of the array. So as long as small n starts somewhere at the beginning, and as long as that is not equal to large N, that means we've still got something left to process, so the loop will continue. As soon as small n reaches large N, the loop will stop and we'll stop processing. So inside of our loop, we'll know that, well, inside P, our invariant definitely needs to be true, and inside the loop we know that small n is not equal to large N. We'll have the loop body, which we'll signify here with S1, again just a label. Now once S1 executes, the only thing we know to be true is our invariant P. And then the loop will finish, and after the loop finishes we'll know that small n is going to be equal to large N, which actually gives us back our original post condition, which I can't write underneath here, I'll just write it out here. So we would have all true is equivalent to, for all I I greater than or equal to 0, less than n. Why large N? Well, now that the loop is finished, small n is now back equal to large N, so we can write large N in here. And then we'd have f dot I equal to true. So that's our outlined solution. And if you notice with the outlined solution, the bits that we've got left to do are, well, we have to figure out how to initialize our variables, and we have to figure out what's going on here in our loop body. And we'll do that next. So in our initialization of our variables, we've got two things to do. We have to figure out how to initialize the variable all true, and we've got to figure out how to initialize n, our loop counter variable, the thing that drives our invariant. So we can do two things here. We can initialize or come up with an initial value for n and work it out and figure out then what all true has to be, or we can substitute a value in for both at the same time. So what we're going to do just in this example is we're going to suggest that n becomes equal to 0. Now, is this a guess? No, it's not a guess. It makes perfect sense because we're starting our processing at the beginning of the array. How do we know that? Because we replaced large N at the beginning to create our invariant, thereby processing the array from the beginning to end. So if I want to start at the beginning, I have to set N equal to 0. So this is an educated guess. It makes sense under the invariant that we're using and the steps that we've taken previously. So we're going to initialize N to 0. And then we'll figure out as we go through the derivation what all true should be. So let's do that. So we need to write out our invariant. So our invariant is, as we had it before, both parts P0 and P1, and we're going to substitute N becomes equal to 0 into our invariant. So if we have a look, N appears here and it also appears here. So basically we're just going to substitute the 0 into this N, and we're also going to substitute the 0 in for this N. So what we say is just true. Substitution. We get all true is equivalent to, for all I greater than or equal to 0, less than, and remember this N is going to become a 0, so we have a 0 here, and then we have f dot I equal to true, and the N here becomes 0, so that gets a 0 there, and that's it. That's the substitution done. Once we do the substitution, the very first thing we should look at is the range that we have for I. Because if we look closely at this range, we will see that it says that I is greater than or equal to 0 and less than 0. And I cannot be greater than or equal to 0 and less than 0. So this is a contradiction. This range is false. It cannot happen. There's no value for I that will satisfy that range. So the very first thing we apply to this now is we say, well, that's a contradiction, isn't it? So we can say contradiction. It's just really plain old logic, really, isn't it? That I cannot have a range there, so there's a contradiction there. And we can say all true is then equivalent to, for all I, oops, well, it's a contradiction, so why am I writing out the range again? It's actually going to be false, because it's a contradiction. So I can write in false there, and I have f.I equal to true, and the rest of it hasn't changed, so I can just continue to write that out. So the next thing we need to look at is how does for all operate over an empty range, over this range of false? Well, if you've looked at the summary of the sequence operators, you'll know that for all over an empty range is true. So we can say for all, and we have an empty range, and we get all true is equivalent to, so this is an empty range, and for all over an empty range gives us true, so this whole part here becomes true. So we get true and zero greater than or equal to 0 less than or equal to n. Okay, so we have all true is equivalent to true and this bit. Okay, so what is this bit over here, this 0 greater than or equal to 0 and 0 less than or equal to n? Well, if we break that down, we can use the law of excluded middle, and that gives us all true is equivalent to true and 0 greater than or equal to 0. So what we're doing really is splitting this up, and 0 less than or equal to n. Now we know that 0 greater than or equal to 0, that's true, so we can say in the next step, we'll just do a couple of steps in one go. So by the laws of constants, 0 greater than or equal to 0 is true, and we know that we were told at the very beginning of the program that n is greater than or equal to 0, so this is also true. So we know that we were given n greater than or equal to 0. So using those facts, I know now that that's going to be true, and that's going to be true, and all true will end up as being true. So we have actually derived the solution for how to initialize our all true variable. So we can set that up here now, and we can say that all true at the beginning of the program should be equal to true. And we did that by substituting the value in for n. We said that it makes sense to set n equal to 0, and when we substitute that in, we get out the value that all true should be. Now I could have substituted both of those values in at the same time and I'd just get a result of true. Either way is fine. You could have substituted true in for all true, and as you work down through the derivation you'd end up with true equal to true, which of course would be true, and the outcome would be fine, it would be all true, proving that those initialization values would actually work. So then really in summary, for S0, S0 then is n will become equal to 0 at the start of the program, and all true will become equal to true. And that's how we'll initialize our variables. The next step is to derive the loop body. So we move on to deriving S1, the loop body. And in order to do that, we need to focus in on what happens to n in the loop body. N, remember, is going to drive our loop, and it's driving our invariant. So something is going to have to happen to n in the loop body. If we remember, the loop that we have is do n not equal to large N. So something has to happen to small n. Remember that we initialize small n to 0. So something's going to have to happen to small n to make it approach large N and ultimately be equal to large N in order to break this loop, to stop the loop from looping around infinitely. So what do we do to n in order to progress it towards large N? Well, it makes sense to suggest that small n would become equal to n plus 1, just to simply increment it, just to add 1 to n every time around the loop. And in order to test that out, we're going to substitute that into our invariant. So when we're dealing with S1, the loop body, we only take the P0 part of our invariant. We leave the P1 bit out of this because it really doesn't make sense to substitute that into the P1 bit. It really just kind of makes sense to substitute it into this part of the invariant, because this is the part of the invariant that's going to do all the work for us. So when we substitute n becomes equal to n plus 1 into this, again, it's just literally straightforward substitution. So we have an n here, and so where there's an n, we put in an n plus 1. Literally replace that n with n plus 1. So let's do that. So we'll have all true for all I and then it will be I less than n plus 1. F dot I equal to true. Okay, the next step in our derivation will be to have a look again at this range that I has, and it says I greater than or equal to 0 less than n plus 1. Well, that's not very helpful. What we need to do with this is we need to focus in on the element that we're currently processing. At the moment, this is all bunched up into one big group here, I greater than or equal to 0 less than n plus 1. So what we need to do is separate out what we've previously processed and what we're currently processing. If we draw a small diagram, it might help to just illustrate this point. So if we have a look at our array that we're processing and we take a snapshot in the middle of processing, n will be here, 0 is there, large N is up there, and this section is processed. And this section is what we've got left to process. So what we're saying here is that separate this statement out into what we've previously processed and what we've got left to process. And in particular, focus in on this element here, the one that we're currently processing. And to do that, we use a special rule called the split off rule, because it allows us to split off what we've previously processed and focus in on what we're currently processing. So we're splitting off everything up to I equal to n, up to that. Okay. So to apply the split off rule, this is how it works. We say all true is equivalent to, for all I greater than or equal to 0, less than small n, and we drop the plus 1 because we'll deal with that in a second, and we say f dot I equal to true. Now everything up to n here, where I is greater than or equal to 0 and less than n, all of that range is here, this part of the array here is what we've previously processed. So I'm going to bracket that off to signify that. And in the split off then, because it's a for all symbol that we're using, in our split off it becomes an and. And again, you should look at the sequence operator summary video to go through all of the different split off rules that apply for each of the operators that we use as part of this course. So because it's a for all, we use an and we're going to split off f dot n, because this is what we're currently processing here, the element that we're currently processing, and of course it's f dot n equal to true. Okay, so now that that's what we've got, we have this bit in the brackets and we have an and we have f dot n equal to true over here. Well, what we do then is we just kind of use a bit of common sense and we say, well, this follows from our invariant p, because what we're saying here is it follows from our invariant p that what we've got in the brackets, this part, and what I've shaded in here in the diagram, all of this bit, well, where's the answer for that bit going to have been stored all the way along if we take this snapshot in the middle of processing? Well, all of the values for this part of the processing that we've done, they will be stored in this variable here, all true. So all true, in effect, already has the answer to this segment of the array, because it's already processed. We've processed all this part of the array and we've stored the answer so far in that variable all true. So if all the values in our Boolean array are true up to that point, all true will be true. If there's some false ones in there, then it's going to be false. So all true holds the value of what we've previously processed. And this bit in the brackets is what we've previously processed. So we can rewrite that and simplify that as all true then is all true and f.n equal to true. And that's the answer. That is the loop body. So then S1, our loop body, is given by all true is equal to, becomes equal to all true. I'm not going to have room to write it all on one line, and f.n equal to true. And of course we can't forget that the loop body also needs to increment n, because that's what got us there essentially. That's how we ended up with our solution. By focusing in on what needs to happen to n, we actually figured out what needs to happen to all true. So all true will become equal to all true and f.n equal to true, which is just a simple Boolean expression, so that if all true is true up to that point, if we get another true, it will be true and true, which will remain true. If f.n is false, we'll get a true and a false, and all true will become false and will remain false then for the remainder of the processing of the array in all of this space here that we've got left to process. So we can combine everything together now into a complete solution, because we have both the S0 bit, the initialization bit, and the loop body. But just before we do that, we're going to have a look at proving that the program will terminate. So to prove termination, or to prove that the program will terminate correctly, we need a couple of bits of information. We know that the guard on our loop is do small n not equal to large N. So small n has to progress towards large N, and we looked after that in the loop body by saying that small n was going to become equal to itself plus 1 every time around the loop. We have a bound function which says large N minus small n, and we need to show that that bound function is a decreasing function. So why is our bound function large N minus small n to begin with? Well, if we draw a little diagram, we'll see that we have n here, we have 0 here, small n started at 0 and works its way up, because we add 1, add 1, add 1 to it, and it eventually will reach large N. So it's progressing towards large N. So small n is moving in that direction towards large N. It starts at 0 and moves its way up. So the bound function of large N minus small n, that means we're going to be taking an ever increasing number, small n, away from something that's staying in the same spot, and that will give us a decreasing function. Now we know that small n starts at 0 because also, remember, going back to the very first thing we did in S0, we figured out that initializing n to 0 was the right thing to do. So all of these bits of information have already been put together. They've already been proved, and we're bringing them together now into the proof for our termination to show that the program will terminate correctly. There are two parts to this. First of all, we have to show that initialization will work, and then we have to show that we make progress. and then we have a decreasing function. So the first part is to take our bound function. So we have n minus small n, and we take the expression that was stated about n at the beginning of the program and we add it on to that. If you remember, at the beginning of the program we were told that n is greater than or equal to 0. So to test it out against our termination, we actually include this bit. See this greater than or equal to 0 bit? We include that in here as well. And we look at what happens to n in the initialization. And n is initialized to 0. So we simply substitute that in here. So through substitution. I'll just write that out shorthand. So through substitution, what we're going to do, wherever there's a small n, we're going to substitute in a 0. So we end up with n minus 0 greater than or equal to 0. Okay, n minus 0 is pretty straightforward, but let's be complete. So by arithmetic, we know that n minus 0 is n, so we end up with n greater than or equal to 0. And of course that follows from what we were given, n greater than or equal to 0. So that works out. Once we get something that satisfies our initial assertion about n at the beginning of the program, that will work out fine. The next part that we need to do, and I'll just have to rub out some of my diagram here. The next bit that we need to do is we need to show that it's a decreasing function. So in order to do that, again we take our bound function, which is n minus small n, and we need to look at what happens to n in the loop body. So that is n becomes equal to n plus 1. And again we substitute this in. So wherever there is an n, we're going to replace it with n plus 1. So this becomes n minus, and because we're mixing minuses and pluses here, it's easy just to bracket this off. So it's n minus n plus 1. Okay, so, well, how do we simplify that? Well, by arithmetic, that is the same as saying n minus n minus 1. Okay, how did we get that? Well, if I add 1 to n and then take it away from large n, that's the same as taking small n away from large n and then taking another 1 away. And the reason we write it out like that is because it's nice and convenient. It makes a little bit more sense this way, and it also shows that this expression n minus 1 is got to be less than n minus n, our bound function. And this shows that it is a decreasing function because it will decrease every time around the loop. If we go back to our little diagram, we'll see, okay, 0 here, n here, and we've got a snapshot in the middle, small n is here, and small n is moving in that direction all the time. And that is because the space that we've got left to process, this space here between n and large n, is shrinking all the time. And that is because of this n minus 1. That space is shrinking by 1 all the time, And this space, the space that we have already processed, that space is actually growing by 1 all the time. So it's a decreasing function in terms of the space that we've got left to process. And that's a good thing, because we want that space that we've got left to process to eventually be of size 0, to show that we've processed the entire array. So now that we've assembled all the bits, it's time to write out our complete solution. So when we're writing out our complete solution, it's just a matter of going back to the specification and just filling out the bits that we've derived. So I've already started to write out the complete solution here, but really the only bits that I've written out are just really copying the specification back out again. So down to here where we have declared our variable all true of type Boolean, we've also got another variable that we've added to the mix here, and that is the variable n. So n, of course, is going to be our loop counter variable, so that's going to be of type int. And then we have to initialize both of those variables. So we know that all true from our derivation was initialized to true. And I'll just do our initializations on one line here. So an n was initialized to 0. The next thing that we have is our loop, and we know that our loop is do n not equal to large N. And inside our loop then we had all true becomes equal to all true and f.n equal to true. And of course don't forget to increment n, because otherwise we will have an infinite loop and the loop finishes. And after the loop finishes, we know that small n will be equal to large N, and that gives us back our original post condition where we can say all true is equivalent to, for all I greater than or equal to 0, less than large N, f dot I is equal to true. And that is our complete solution. So really this bit is what we derived. So we call that S0, and of course the loop body, we also derived that, and we call that S1. So really it's just a matter of filling out the extra bits that we've done as part of our derivation. Of course we also introduced our new variable n here, and we're including that as well. So when you write out the complete solution, it's really just fitting those bits of the jigsaw puzzle that you've derived back into the specification. And that's it. That's the complete solution for our problem.